Welcome back. I think where we left off last time is you all were supposed to do number 4 on your own. Well, I just want to check in and make sure, sorry, I know my camera abilities kind of suck. I just want to make sure that you guys have done that, and I want to walk you through it in case you're stuck. So let's look at number 4. The truck in the previous problem is towing a trailer with wheels that have a diameter of 48 centimeters. So remember, I asked you to convert that to meters, which will be 0.48 meters as the diameter. Also remember, when you are using radius, you're going to have that. So instead of 0.48 meters, you're going to use the radius as 0.24. So let's go on. How does the linear acceleration of the trailer compare with that of the truck? Well, let me show you what I've written out. Because the linear acceleration is equal to velocity over time, or the change in velocity over the change in time, well, their linear accelerations are going to be the same. If you are towing something, it's not going faster than you. Otherwise, that's bad. That would cause a wreck. And it's not going slower than you because it has to keep up with you because of the hitch. You've got a hitch attached to whatever you're towing. So the linear acceleration is going to be the exact same. And that's just how fast are you accelerating on the road. But part B asks us something totally different. And it wants us to know, how does the angular acceleration compare? Well, that's different. Because basically, for angular acceleration, you're looking at how many times do these wheels revolve. So the truck, we were given in the problem that the truck had an angular acceleration of 5.23 radians per second squared. So if you're asking me, hey, where did she get that? That was given to us in the previous problem. Since the trailer has to keep up with the truck that is pulling it, are the smaller wheels going to be the same number of revolutions, or do they have to make more revolutions to keep up? Well, obviously, they have to make more revolutions, and I was trying to think of a way to explain that, not with wheels, but so here's what I came up with. It's like if Danny DeVito had to walk side by side with, let's say, Abraham Lincoln, and they are walking the length of the gym side by side, holding hands if they can. And if they reach the other end of the gym at the same time, who had to take more steps? Well, obviously, Danny DeVito, his legs are shorter. It's the same idea with angular acceleration. If you have a smaller radius, you have to make more revolutions to keep up. Just like shorter legs, which I know this, you have to walk faster to keep up with people. So let's look at that mathematically. So if I look at it mathematically, we've got the angular acceleration, that's the little Jesus fish symbol of the truck. Well, we know that they gave it to us at 5.23 radians per second squared. Now I'm going to show you how radians kind of pop back into this. And again, we know physics can be weird. I accidentally put the diameter in, so I'm sorry. We're going to use 0.24 as the radius. And we also solved in the last problem that the linear velocity is 1.85 meters per second squared. Now we're going to put that over our radius of the trailer wheel, which is 0.24 meters, Now, because we are talking about revolutions, we're going to stick radians in as our unit. I know that feels crazy. So the angular acceleration of the trailer's tire or wheel, I forget what the wheel, is actually 7.7 radians per second squared. And all we did to find that is use the 1.85 meters per second squared. It's the linear acceleration. divided by the radius of the wheel will give us the angular acceleration of the trailer's wheel. And so that's what you get here. It's 7.7. In a way to check yourself, I want you to think about this. This truck tire is bigger. It's got a larger diameter than the trailer tire. Well, it makes sense. This is going to be smaller because it's larger. The truck tire only has to go around once, whereas the trailer tire goes around almost, it takes about time and a half to reach that same thing. So it has to go a little bit faster. Let me quit talking about that because I really don't want to confuse you. And if you are already confused, let's try one more thing. It asks you in the challenge questions about replacing a tire on your car. Excuse me. You replace the tires on your car with tires that have a larger diameter. So after you change the tires, how will the angular velocity and the number of revolutions be different for trips at the same speed over the same distance? Well, it's the same thing that I was talking to you about Danny DeVito versus Abraham Lincoln. So you're going to take your Danny DeVito car tire and you're going to replace it with an Abraham Lincoln car tire. So a bigger tire. Does it have to make the same number of revolutions? No. So the number of revolutions will go down for trips at the same speed over the same distance. So the smaller the tire, the larger the angular acceleration has to be. And the larger the tire, the smaller the angular acceleration is going to be. So that's an inverse relationship. All right, I'm going to pause this for now. Okay, let's take a look at the moon question. The moon rotates once on its axis in 27.3 days, and its radius is 1.74 times 10 to the 6 meters. Well, the first thing I want us to do is take that 27.3 days and use, oh gosh, it just flew out of my head. You know what I'm talking about. And we're going to use dimensional analysis to convert it to seconds. So before we ever do anything else, let's do that right now. All right, so here I have what we need. So using dimensional analysis, I want you to write this down. So if our time is 27.3 days, you start with your given. And now 1 day is equal to 24 hours. 1 hour is equal to 60 minutes. And 1 minute is equal to 60 seconds. So I'm going to give you a few seconds to write that down. And let's see what we get. No, really, I'm going to wait on you. Okay, so you should have gotten 2.36 times 10 to the 6th seconds. Okay? And we've also been given the radius, and the radius is 1.74 times 10 to the 6th meters. So let's do this just together. Let's just do it together. So come back over here, and we have, what is the period of the moon's rotation in seconds? Well, you just solve for that. That is your 2.6 times 10 to the 6 seconds. All right? Sorry, I'm trying to keep it in focus. I don't know what is going on. And then B. Whoops. Sorry. B is, what is the frequency of the moon's rotation in radians per second? Well, you don't actually have to use the frequency formula to get radians per second. We're going to do it just like we've done everything else in radians per second. We are going to solve for 2 pi divided by our time. And so if you do 2 pi divided by 2.36 times 10 to the 6 seconds, you will get 2.7 times 10 to the negative 6 radians per second. And I'm so afraid that if I would explain how that works with frequency, I'm afraid that I would confuse you. But I'm just going to ask you to trust me that you can simply find the angular velocity, and that'll give you the same answer for frequency. All right, you got to trust me. Let's take a look at C. Let's see. A rock sits on the surface of the moon's equator. Wonderful. What is its linear speed due to the moon's rotation? All right, so we're going to sit at the moon. Okay. So we all know speed is the same as distance divided by time. Well, all we have is the radius, right? So my little math geniuses, do you remember how to go from radius to circumference? Because if you're sitting on the surface of the moon, we want to see how long it takes you to go all the way around in the given time that we said, that we've already calculated. Well, we know that radius is the 1.74 times 10 to the 6th. And to solve for circumference, we use 2 pi r. So we're going to do, this is how I got 2 pi r. I did 2 pi times the radius, and that gave me 1.09 times 10 to the 7th meters. That's how I calculated that, just 2 pi times 1.74 times 10 to the 6th. This is the number it gave me. Now, we're going to divide distance by time, and then you should get this, 4.63 meters per second. And I think we're going to stop there together. What I'd like for you guys to do is, let's see here, we're going to skip part D because I don't care about standing on the Earth's equator. Let's look at angular displacement, because we've done a problem very similar to this, so I think you guys can do this on your own. So today, you have a movie that lasts 2 hours. During that time, what is the angular displacement of each of the following? The hour hand, the minute hand, and the second hand. So in 2 hours, remember, your hour hand is going to move a certain amount of time, the minute hand, and the second hand. Now, we did these in reverse order at the beginning of our practice the other day. So if you need help, you know, I'm here all day, every day. So just let me know. And I will talk to you guys later. All right, bye-bye.